Now, our problem is to solve the classical birthday problem, but for even larger sample size. The sample size now, say, is 10,000 persons. That is good. So the first cell says the import libraries, right? So let it go. So now I have defined again the probability P, 1/365, number of persons, the sample size 10,000, and mu value is mean value is NP, right? And I have defined the X range values, right? For calculation of probabilities, it is mu minus 15 and mu plus 15. I have made that number integer because in the A range function, I require the values to be in integer. So if I run it, and I have used the separate print commands to print mu value and X. So mu value is 25, which is greater than 20. Okay. And X values have been generated from 12 to 14. So that is the vector. I will only compute probabilities for these X values. And that's my assumption from my experience that with this vector, I will be able to pick up the most frequent events occurring in this whole distribution. Actually, all the values for this problem, all the values for X 0 to 10,000 now, they are possible. Like finding among 10,000, no person with the birthday on a particular day, one person having birthday on the same day, and in very unlikely case, all 10,000 persons having the same birthday, right? So it is very unlikely if you collect people at random. But if you have already informed them that only those persons are invited who have birthday on 25th of December, in that case, you would be able to touch that event, that particular event, with the probability, say 10 raised to the power minus 20, around 10 raised to the power minus 20 probability, right? Well, you have the software, you can calculate that event. But let's do that at the end of this demonstration. So Poisson probabilities will be computed. You have to provide the vector and you have to provide the mu value. The only parameter required for describing the Poisson distribution. And therefore, in this problem, we are using again this Poisson distribution as a mathematical simplification because our problem is the binomial one, right? So this vector has been generated. Now, for this problem, we can also use the normal approximation. So in normal approximation, we can use the same mu value and we can define sigma as square root of mu value. We know that the normal distribution is a distinct distribution with distinct value of sigma, right? Not defined in this fashion. Now for that one, here is the normal approximation. I have defined sigma value, right, as square root of mu. And now the calculation of normal distribution. Here the expression is the normal. I have used CDF, right? Because normal distribution is a continuous distribution. It is not defined on point basis. It has to be defined on interval basis. So to define, say, a number 12, I have defined a number 12.5 and a number 11.5. So from that integral evaluation, so that probability will be computed. And now for comparison, so this will be computed. And then the fourth step is to do the comparison, define an error vector. So that is done. And the maximum error for that vector in the probabilities computed from Poisson approximation, and that is up to the digits 2 decimal places. And a similar part, similar type of program that I wrote previously to compare binomial and Poisson probabilities. So it is there. It's here, right? So the error is 0.0005. So it is reasonably approximate to compute Poisson probabilities using normal approximation, right? And these are the probability summations for events. So it is almost, it's very close to 1. If you consider some more events near the ends of the distribution, right hand and the left hand, so you will be able to explore that one as well. And here is the generation of this picture. So I have plotted the Poisson probabilities as bar graph to make a distinction between the individual events defined in Poisson distribution. And for normal distribution, I have used the attribute of line plot. I have also defined the line width as 3. You can change that number. And I have defined the legends to highlight, since there are uh, two characteristics being shown on the graph. So it's there. So that is the graph generation. To make it a fresh calculation, let me change this value. It's really a fresh calculation, right? So this is the use of normal distribution and the probability calculations from the function provided by the SciPy in Python.